motor-driven valves at once. A large valve requiring a lot of power to operate does not necessarily require a powerful motor to do the job. If a system of gears is attached, the power needed to operate the valve is reduced, and the valve can be positioned manually. Sometimes valves must be located in areas that are hard to reach. When this is the case, an extension stem or a sprocket wheel and chain can make the valve easier to operate. Regardless of what type of valve operating mechanism is used, valves should always be opened and closed gradually. This will prevent sudden pressure and temperature changes from occurring in the piping. For example, if a valve is suddenly snapped shut, the abrupt change of flow causes pressure surges that can damage the valve and, in extreme cases, even rupture the pipes. This is known as hydraulic shock and is primarily a problem in lines controlled with quick opening valves. Some large valves are often difficult to open because one side of the flow control element is under much more pressure than the other side. These valves are usually equipped with an equalizing line. The valve on the equalizing line is always opened before the main valve. This allows pressure to equalize on both sides of the flow control element, making the large valve easier to operate. Sometimes a valve will become stuck because the moving parts are corroded, excessively worn, or fouled with solid materials. In these instances, it may be necessary to use a valve wrench or cheater to operate the valve. Wrenches are available in a variety of different styles and sizes. To prevent damage to the valve, check the manufacturer's specifications concerning the wrench use before using a valve wrench. Choose the correct size wrench and securely attach it to the hand wheel or spokes so that the wrench will not come off when force is applied. When applying force to the wrench, make sure your weight is evenly distributed so you don't fall when the valve opens. Wrenches should always be pulled towards you to prevent ramming your fingers when the valve gives. If you encounter difficulties or have any questions, notify your supervisor. When closing a valve, you should avoid using excessive force because this may damage the seats or the flow control element. This is especially true for gate valves in high-temperature service. After the valve is closed, it cools and the valve body contracts. If the gate is already jammed into the seats, contraction of the valve body may cause the gate to bind. Many valves, such as gates, plugs, and globes, require periodic lubrication for smooth operation. On outside stem and yoke valves, the exposed threads should be cleaned and greased at regular intervals. The internal valve parts are usually lubricated with a grease gun or by inserting a stick lubricant into a special fitting. All valves with stems have a stuffing box that is filled with a sealing material called packing. The packing material is compressed by a gland to produce a leak-proof seal around the stem. If packing leaks occur, they can often be corrected by tightening the packing gland nuts. Eventually, however, the packing will be compressed to its limit and will have to be replaced. Leaks sometimes develop between the valve body and the bonnet, or the piping. These leaks are often caused by a gradual stretching of the bolts that hold the various parts together. They can usually be fixed by simply tightening the bolts. Whenever you're dealing with leaks, avoid contact with the leaking fluid because it can and often does pose a hazard. Let's review the material on valve operators and operating procedures. Now, please stop the tape and turn to workbook period number 3. So far in this program, we have mainly focused on valves that are operated manually. either by hand or by motor. In any manufacturing or process industry, however, there are applications where it is desirable or necessary for valves to operate automatically. When automatic operation is desired, a control valve is used to regulate the flow of fluids. The body of the control valve can be designed like any of the manually operated valves we discussed earlier in this program. But instead of a hand wheel or a lever, a control valve is equipped with an actuator that moves the valve stem. The actuator receives commands from a controller telling it how to position the valve. The controller sends signals in the form of compressed air, hydraulic fluid pressure, or electricity that automatically move the valve into the desired position. This control valve is powered by an actuator that receives compressed air signals from a controller. The actuator contains a diaphragm and a spring. Air pressure from the controller tries to push the diaphragm down. The spring tries to keep the diaphragm up. When air pressure against the top of the diaphragm exceeds the force of the spring, the valve stem is pushed downward and the valve closes. This type of actuator can be used for both throttling and on-off service. In some instances, the maximum compressed air signal from a controller is not able to move the valve stem fast enough or hold it in a steady position. When this is the case, a valve positioner is installed on the valve to help the actuator position the valve stem. Here's another type of control valve. It has a solenoid actuator. The solenoid consists of a spring, a coil, and an iron core. Electrical signals from a controller move the valve. When electrical current is sent through the coil, a magnetic field is set up that pulls the core upward and closes the valve. When the current stops, the core is pushed out of the coil by the spring and the valve opens. Because of its design, a solenoid-operated valve can only be used for on-off service. Solenoid valves with heavy springs find important duty on fuel supply lines to boilers and furnaces where they snap shut quickly if electrical power fails or other safety trips are activated. If throttling action is required, a motor-operated actuator can be used to position the valve. The motor is connected to the valve stem through a system of reduction gears and is capable of moving the valve into any desired position. This control valve is operated by a hydraulic actuator which contains two chambers that are separated by a piston. When more hydraulic fluid is directed into chamber 1, the piston is moved to the right and the valve closes. Directing hydraulic fluid into chamber 2 pushes the piston to the left and opens the valve. Hydraulic actuators can provide on-off or throttling service. Most control valves are equipped with some type of valve position indicator. These indicators are usually attached to the valve stem so that an operator can quickly determine the actual valve position. In this program, you've seen the various types of valves that can be used in piping systems to control the flow of fluids and gases. We've looked at how these valves are designed and discussed what kinds of service they are set up to perform. We showed you mechanical valve operators, such as gears and sprocket wheel and chains that can make a valve more accessible and easier to operate. You also learned some basic operating procedures that should be followed when opening and closing a valve. Finally, we introduced you to valves that operate automatically in response to a signal from a controller. These control valves are positioned by an actuator which is powered by compressed air, hydraulic fluid pressure, or electricity. This concludes our program on valves. Now go to your workbook and complete the final section. Thank you for watching.